Hi, this is Mr. Mitchell with a video about motion. Here are some questions for you about motion. Please write them down. Motion. If you sit in a chair motionless, kind of like this guy must have done, you're still moving. You don't realize it, but as far as the solar system is concerned, you have the Earth, which is rotating around the sun, and you're on the Earth. So just makes sense that you're moving, though it looks like you're completely motionless. And the reason we look motionless as we sit in our desk or in our chair is because we don't have a reference point for Earth's movements in space. And for us to know that we have had motion, we have to have some kind of reference point. Look at this kid right here, some kind of time-lapse photography. All the stuff around him, the grass, the sand, it of course is staying still. But you can see how he has moved over the individual slides. So motion is the change of distance over a given time. Now, I'll give you an example of a school bus. The school bus here has been driving along, but the tree is motionless. So if you had seen this scene 3 seconds earlier, the bus would have been way back out to the left of the tree. But if you look 3 seconds later, you can see it's now to the right of the tree. You have to have some kind of reference point to know that there has been motion. And motion, of course, is the change of position over time. But a change of position tells you that motion took place, but it doesn't tell you how quickly the object changes position. And that, of course, is a term called speed. And speed is going to be distance over time. You know, we typically think of speed as miles per hour, but speed in scientific terms is usually going to be in meters per second. And if you happen to get speed in miles per hour, it may be something you have to convert over. Let's have a couple of practice problems. What's the speed of a sailboat that's traveling 100 meters in 120 seconds? Let's see. Speed is equal distance over time. So speed is equal, the distance is 100 meters, and meters is the unit we want to use. And it's over 120 seconds. So hey, that works out pretty well. You just divide 100 by 12, which of course is going to reduce to 10 over 12, which is going to reduce to 5 over 6. So that would mean, let's go to my handy dandy calculator here on the dashboard, and we'll go 5 divided by 6 equals 0.833. So we'll have 0.83 meters per second. Try this next one. Baseball is thrown a distance of 20 meters. What is the speed if it takes 0.5 seconds to cover that distance? Speed equals distance over time. And distance is going to be 20 meters. Make sure that you do put the unit there. And it's over 0.5 seconds. So let me go back to my dashboard here. And we'll have clear 20 divided by 0.5 equals, and we're looking at 40 meters per second. That's what we have for that one. So that's how you calculate speed in meters per second. Now, you may notice that speed, you've known this, speed is not constant. If you are running in a race for the first, and here's a distance over time graph, you'll see some more of those. For the first 10 miles, not 10 miles, but say the first 10 meters, you're running very fast. But you're obviously going to end up getting slower, and for the next little chunk of time, you're not going to run as fast, and then by the end, you are kind of standing still. So that's not constant speed. You may be at far faster meters per second in this first part of the race than you are at the end of the race. So it's better to calculate the average speed, because speed is typically not constant, especially when it's talking about something that has to do with humans. If speed were constant on a graph, it would be just like this. It would be a complete what do you call that, diagonal line on one of these graphs, and I think it will look better whenever I take that off of there. You know, whenever you have a complete diagonal line, that would be at the distance over time is constant, but you know speed is not constant. But look, that also gives a chance to talk about these slopes here. If you have a slope on a distance time graph that's like that, you have a faster average speed. And if you have a slope on time that looks like that, you have a slower average speed. So I figured I'd get that in there while we're there. But speed is not constant. And there's even another term that we use more than speed, and that is called velocity. Now you see some formulas up here. You've already seen this speed formula. Speed is distance over divided by time. The only difference in velocity formula is something called displacement. Now displacement is literally how far something is from something else. And what you have with velocity is that you have a certain direction. With speed, it's how fast you're moving. With velocity, it's speed and direction. Speed and direction. How can we use this, for example? Let's say there's a running back who gets the ball on the 30-yard line. He's trying to score. Say he runs around to the left side, and he's about to get tackled, so he ends up going back to the right side. He ends up going even back 5 yards and ends up scoring way back here in the corner. He ran far more than 30 yards. But to calculate, the number we would use is 30 yards because we typically use the velocity. If we'd calculated distance, I guess he probably ran about 50 yards just to get to the end zone. So if we were calculating speed, we'd have the distance in there. But generally, we're going to be calculating velocity. So that's why we have the term displacement. The ball literally went from the 30-yard line to the goal line. So in velocity, that is 30 yards. Even if they ran more than 30 yards. Do you get that? Maybe you do. Let's talk about these graphs. I guess the first thing to talk about is vector. One term you will hear a little bit with velocity and with some other terms that it is a vector. Since most items don't travel in a straight line, you may hear of this term vector. See, speed isn't a vector, but velocity is. So velocity, no matter whether it's true or not, is represented by a straight line. Speed is not. So as a result, velocity is more true here at a constant speed. If someone were actually speeding up and then going slower and then speeding up again, if you in calculating average speed, it's like calculating the displacement, which is the velocity. So know this term, that velocity is often used as a vector term, and you'll find some other things because it has distance as well as how fast something is going. So just on these graphs here, if you have a straight line, that means an object is stationary. You do not have the motion. Here you have something that is decreasing velocity. If it is curving downward, it is slowing down. Curving downward, it is slowing down. I shouldn't have put this one here because we haven't used the term negative velocity yet. But that also means that if it is going up, then it's speeding up. And you can see the term here is accelerating. And we're going to talk about accelerating in just a second. In this part, we have a line more like what we had here. So that is where you had constant speed. And here is where I guess you are, say, decelerating. And when you have the straight part of the line, that is when you're stationary. So let's get to that word, acceleration. There's a measurement called acceleration, which accounts for the different rise and fall of speed. Acceleration is how quickly velocity changes. If there's no change, there's no acceleration. So if we had one of those graphs that had constant speed, there was no change. So that is no acceleration right there. You have to have a change in speed. Now that change in speed can be faster or slower. Here you have people who are on the starting line. Here's someone who is just coming off the starting blocks, going incredibly fast down the track. And here's someone who's probably started a long time ago and going much slower, probably just barely able to keep running. Naturally, there's more acceleration here, but just because her speed is changing, that gives her a degree of deceleration. Now, we're going to call that negative acceleration. Acceleration is a vector, can be represented by a vector, just like velocity, and not like speed. So, let me tell you something about positive and negative acceleration. Positive acceleration, we have this vehicle going 50 miles an hour and it's going up to 70 miles an hour. That is positive acceleration. Negative acceleration doesn't sound like it should really be acceleration. It sounds like it should be slowing down, but technically is acceleration, but it is going to be in negative terms. You might call it deceleration, and sure enough, there is a formula for that. Change in velocity over time. Let's just see if we can do one or two of these. An airplane accelerates down a runway for 3.2 meters per second square for 32.8 seconds. Okay, determine the distance. Okay. We have probably, let's see if we can go to this one first. Yeah, this one's asking for distance, so I'm going to use it second. I probably should have put it second here. So let's kind of put that one on hold and go here. A race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second. So we have acceleration equals the change in velocity. So what is the change from 46.1 to 18.5? Let's see, we are subtracting here, so that is what, 6? Make that a 5. Oh, that is what, 7? And make that a 3. So we have 27.6 meters per second. That is the change in velocity because we're going from 18.5 to 46.1. So acceleration is change in velocity, which will be 27.6 over what? And here's the time interval, 2.47 seconds. So we have acceleration in meters per second, and we have distance traveled, our time, in 2.47 seconds. So we're going to run out of time, but it's just a matter of plugging in 27.6 divided by 2.47. It's going to be something like around 14, and that would be in 14, whatever it is, meters per second square. Okay, we're doing something different here. The distance traveled before takeoff is going to be, acceleration is going to be initial velocity minus final velocity over the time interval. So if it's accelerating at 3.2 meters per second, you've got the acceleration. And you've got the time in 32.8 meters per second square, 32.8 seconds. So we're going to have to solve for this. How should I go about this? Because we are running out of time. Here's how you do that. You multiply both sides times t. That cancels out, and you have the change in velocity equals